we're ready for part 3. And yes, I know this is not particularly exciting to have to watch video this way. That many of you have said it'd be more exciting if you could actually see me, but sorry, that's the breaks. So we're going to have to continue with this. This last part is actually pretty sweet and simple and kind of cool. You'll be actually somewhat surprised as we go through the rest of the semester how much this particular topic is going to come back to haunt you. With this little idea of what's called an inverse function, we can create some pretty powerful and unique functions in the coming months. So, of course, I first need to take you back to one important question. What was a function? And hopefully you'll remember that a function meant each x-coordinate could only be paired with exactly one y-coordinate. Now, I know when we talked about this when we were reviewing for the semester test, it seemed to go fairly easily. And you'll hopefully remember that on a graph, how do we know, if you look in that top right corner, how do we know whether that graph is a function? And hopefully somebody's saying the vertical line test or the pencil test, and you would be correct. As long as you can draw a vertical line and always hit just 1 point, it's a function. If you can draw a vertical line and hit 2 points, it's not a function. Most of what we work with are functions throughout most of high school math, but occasionally we do things that aren't functions. In fact, what we will start on next Tuesday, we will have some that aren't functions. But in order to have an inverse function, you have to start with a function. And the concept of an inverse is really, really simple. If you'll notice here, I've got it set up, if function f is all the coordinates x comma y, then an inverse is all the coordinates. Anybody want to take a guess? Well, there's about only one thing you could do with x, y, and that would be to switch them, and you would be correct. An inverse is simply found by switching the x and y coordinates. You write your y's first, then your x's second. So if you take this function I gave you here on the next line with the coordinates negative 2, 3, 4, 7, and negative 5, 11, and I ask you to name the inverse coordinates, all you would have to do is reverse your coordinates. So we would have 3, negative 2, 7, 4, and 11, negative 5. That's all it takes to make an inverse if you're working with the coordinates. So let's face it. How often do we give lists of coordinates? Not very much. We usually work with either equations or graphs. So I want to talk to you about how we find an inverse on a graph. And so I'm going to take our good friend, our favorite of favorites, our handy-dandy, lovely parabola, y equals x squared. And you'll notice down here in the bottom left corner in black, I have our usual coordinates we use to plot a standard parabola. There's our 1, 2, 3, 1, 4, 9. And so I'm actually only going to plot up to the 4s because it gets it's too big that will go off my little graph here. But we would plot 0, 0, 1, 1 on both sides, 2, 4 on both sides, and get our usual parabola. No big deal. Okay. My question to you is, what will happen when we plot its inverse? And how do I find the coordinates of its inverse? Yeah, I simply switch these coordinates. So I'm going to switch them. 0, 0, not much difference. 1, 1, not much difference. 4, 2, 9, 3. Now, there would be one other little change, though, that we have to look out for. We automatically, when we plotted this parabola, we plotted the mirror point on the negative side. But in reality, didn't we really have the points negative 1, 1 and negative 2, 4? And those would make a difference when I come over here and make my inverse, because now I would have 1, negative 1, and 4, negative 2. So if I plot these points, the coordinates I have written here in blue, some of them are going to be the same, but some of them are going to be different. 0, 0 is the same. 1, 1 is the same. 4 over 2 up. If I come down to the ones with the negatives, it's 1, negative 1, so that would be 1 over 1 down, and then 4 over 2 down. What am I going to get? And yes, I get a sideways parabola. It simply took the parabola I started with, and it flipped it. The question is, how did it flip it? What did it flip it over? It's actually reflected over a line. Can you tell where that imaginary line would be that it is reflected over? Well, since the points 0, 0, and 1, 1 are the same, the line has to be going through there. I'm going to draw this imaginary dotted line down the middle here. And you'll discover that that line happens to be the line y equals x. It's the perfect diagonal line that goes through 1, 1, 2, 2, 3, 3, 4, 4. All inverses reflect across that line. Everything that's an inverse goes through that line. Unfortunately, my calibration isn't working so good here because I'm not getting it down the middle of that little gap very well, as much as I wanted it to. But it should actually be right down the middle of that gap. All inverses reflect over that line. If you graph any function and you graph its inverse function, they will always reflect over the line y equals x. So this statement down here, if f and g are inverses, their graph will what? Well, their graph will reflect over the line y equals x. Always. Every inverse and its original function always reflect over that line. If you're taking the ACT test and they give you a graph of two functions and they say, are these inverses? If they reflect over that diagonal line, they are inverses. Okay. You'll also notice I have the words horizontal line test written. What's all that about? Well, did my blue new inverse function end up being a function? Does it pass the vertical line test? And you'll notice that no, this parabola would not pass the vertical line test. The blue parabola would not. Okay, how would I have known by looking at the pink original function, the original parabola? How can I tell that when I reflect it, it's not going to pass, it's not going to be a function when I do an inverse? And yes, the horizontal line test. If you draw a horizontal line across the point through the original function here, when I draw that horizontal line, I hit 2 points. The original function does not pass the horizontal line test. That tells me that when I do the inverse will not pass the vertical line test. When I reflect those points, it's not going to pass. So the horizontal line test actually means if f, the original function, passes the horizontal line test, then the inverse will be a function. In other words, it will pass the vertical line test. So that's a quick way to tell when you're working with a function, if you have its graph, whether or not it's going to have an inverse that's a function. And I can do a really, really quick example here. Suppose I gave you this little wavy graph like that. Does it pass the horizontal line test? Answer would be nope. So therefore, you know that the inverse function, well actually, the inverse of it will not be a function because it won't pass the vertical line test. So that's a quick way how you can tell these things. All right, we're going to move on here to the last screen then and talk a little bit about how you find the equation of an inverse. This is actually pretty sweet and simple. You'll notice I have two steps written up here. if you want to find the equation of the inverse, you have to do what we did there. To find an inverse means to switch your x and y coordinates. In our case, that means to switch our x and y variables. And then you have to solve for y. Now you'll notice over here on the right, I have f of x equals 4x minus 7. And I just said switch x and y. There's no y in this function. There's nothing. You don't see a y anywhere. But you have to remember, f of x is the same thing as writing y equals. So if you see f of x equals, it's the same thing as y equals. So when I say switch x and y, I mean change every y into an x and change every x into a y. Literally change the variables to the opposite. Do not move any of the numbers, don't change any of the numbers, just switch the variables. Now, you simply need to solve for y. How do I get y by itself? Well, okay, I need to add 7 over. That will leave me with 4y. How do I get rid of the 4? I divide by 4. And I'm now down to y equals. What I would like you to do at the end then is change it back to the symbol for inverse and say, hey, my inverse function is really the function x plus 7 over 4. You have found the inverse. That's sweet and simple. Okay, another one here. Actually, I think I'm going to change this and make this into a cube root just for fun. Cube roots as opposed to square roots, even though we haven't really worked with them a lot this year, give you a little pizzazz. Okay, if I say find the equation of the inverse, what do the two steps say I should do? Well, A, number one, I need to think of that as y to start with. So it says switch x and y. So, okay, if I switch x and y, I now have x equals cube root of 2y minus 7. I need to solve for y. Y is inside a root. I can't solve for y if it's inside the root. So how do I get rid of a cube root? Well, if you want to get rid of when you want to get rid of a square root, you square things. So if you want to get rid of a cube root, you cube it. But of course, you have to do it to both sides. So now I have x cubed equals 2y minus 7 because I just made the cube root cancel. And then it's fairly simple to get y by itself. Should I move this 2 first or the 7 first? And yes, I should add the 7 over and then at last divide by 2. Am I done? Is that my answer? Hopefully you said no, because you need to put the inverse symbol back on it to say, hey dude, this is my inverse. And so my inverse function is x cubed plus 7 over 2. All right, our last little piece. You'll notice I have two functions here for you, f and g. And it says, are f and g inverses of each other? This is a cool little thing. Turns out, if two functions are inverses of each other, if you do f of g or g of f, in other words, if you put one of them into the other, and it doesn't matter which one you put into which, you should end up with an answer of x. Not 2x, 3x, not x plus a number. If you get plain old x, they're inverses of each other. So it doesn't matter. You can look at the two functions and go, which would be the easiest one to put into the other. In this case, I think we should put the root over here into something squared because I think that'll work out pretty sweet. So would that be doing f of g or g of f? Remember what the thing I'm putting in comes second, so it would actually be g of f that I'm doing here. And I'm going to put f into g, so I will have my square root of 2x minus 5 squared plus 5 all over 2. You should discover that lots of things will cancel. When I square it, I'll get rid of the square root. And then here comes the canceling. The 5's add up to 0. They cancel. And since they're now out of my way, what else cancels? The 2's. And I am down to a single little x. Since that's what I had left, then yes, those are inverses of each other. It's amazing. All right, in 18 seconds or less here, you all have a lovely, lovely worksheet you should spend the rest of the class time working on. You can also work on finishing your journals. That's really, really important. If you have any questions, I'll be back on Monday. Feel free to call me or text me as well this weekend. Have a great day.